Okay. Homemade taser test 1. Okay, homemade taser test 2. Sounds like the capacitor's winding back up. Turns out Dr. Pepper is not good for tasers. Who'd have thunk it? We've got a little bit of light on the board, and it's coming back on. Alright, well, I don't know if an Ethernet cable was really the best idea after all to make a taser out of, but I might still be able to make something work. This isn't going according to plan. Oh well. Science. Okay, I have officially decided that this is not the best taser in the world. However, it is a very efficient computer destroyer. So, here we have an example motherboard. All you'd have to do is take this standard little Ethernet, plug that into the RJ45 board, or RJ45 port on the motherboard, and this little thing sends about 330 volts coursing through very sensitive electrical equipment. Alright, well, this just wouldn't be fun unless we did a live fire demonstration. So, here we have a slightly used motherboard and our computer destroyinator, and we're going to see what happens when we plug this in to that. So let's take a look. Alright, we're plugged in, and the trigger is right down there. So let's hit that trigger and... oh, you probably couldn't hear that, but it just crackled a lot. Huh. Nice. Well, it didn't work before, and I think it works even less now. So, cool. So, it is a very interesting little board, very simple, but very deadly when hooked up to a computer, such as this one. So, what we're going to do, in the interest of science, is blow it up. So, first step, we're going to hook up the power supply. Here's our 1.5 volt. Hold on. Alright, so, let's try that now. There we go. Now we can hear it. Just gotta wait for the little indicator light to come on. And there it goes. Alright, we've got juice. Alright. Now we take a computer. Turn on computer. Here is the Ethernet cable of death. And let's plug it in and see what happens. Assuming that we can actually... whoa, there we go. That was a good pop. What you gonna do about it, laptop? Uh-oh. Uh-oh, what's this? Oh, fatal error. Oh no. Huh. Well, I guess that laptop's done for. It's a really old one anyway, so I really don't care. That was good though. Let's see what would happen if we do that again. And hit the trigger. Ha! Yep, that laptop is thoroughly dead. Thank you for playing. Alright, we've had some fun, we've blown some stuff up. Now it's time for math and such. Alright, so let's start off with the transformers. So as we may or may not have observed earlier, we have two transformers here, kind of a larger one here and a smaller one here. And this is a step-up transformer and this is a step-down transformer. Now the purpose of a step-up transformer is to take a small voltage and high current and turn that into higher voltage and lower current. The purpose of the step-down transformer is to take higher voltage and turn that into lower voltage, but to take lower current and turn that into higher current. So we end up with Ohm's law being satisfied. So in this particular case, we can see from the capacitor that our final voltage is going to be 300 volts, and by nature of AAA batteries, we know that those run on 1.5 volts. So that tells us that we should be having a conversion ratio set up something like this. This is basically how the ratios are set up. For our voltage, we end up with the final voltage being the number of turns in the secondary over the number of turns in the primary coils, and for the current ratio, it's the exact reciprocal. And so in this particular case, we have 1.5 volts to 330 volts, so that works out to being a 1 to 220 ratio. So that's pretty steep. And so using some math, we see that 1 over 220 equals the number of secondaries over number of primaries. So the number of turns in the secondary coil over 5 has to be equal to 220. So some basic arithmetic tells us that we can see that there are 5 turns on the outside primary coil, so there must be 1,100 turns on the inside secondary coil. That is ridiculous. There is a lot of wire packed up into a very small amount of space there. But that's how it works. The second transformer in this circuit is this little step-down transformer. Now you can see it's a little bit smaller than the step-up transformer, and it does a very similar thing, just completely backwards. What it does is it takes 330 volts coming from our capacitor and turns that into a much more manageable voltage for our little indicator LED light right here. And so the purpose of this little LED light is to tell us when the capacitor is charged, but it wouldn't make a whole lot of sense to send 330 volts down to the LED light, blow the LED right up. So using a multimeter tool, we were able to kind of figure out that this LED light seems to be running at about 4.5 volts, give or take, when the capacitor is fully charged. That's rough estimates based on measurements, but that's kind of our best guess. And this particular transformer here, we can't really see what the how many coils or how many turns we have in the secondary coil, because it's all wrapped up in the primaries. Now, we didn't have that problem with the larger transformer out here because our primary coils are really big and they're on the outside. We don't have to really work too hard to count them up. In this case, though, there are lots and lots and lots of coils on the, or lots of turns on the outside on our primary, not too many on our secondary. So if we're going to say, well, there's about five primary turns on our large step-up transformer, we can guess maybe there's 5 or so, give or take, on our little step-down transformer. So, yet again, kind of using rough math on this. The best we can do without actually taking it apart and trying to dissect it and seeing what we have to work with. But, 5's probably a good number to work with. So, math involved with this. The ratio, using the guesstimated numbers from a multimeter, we figure we have about 4.5 volts, and our 4.5 volts are being created, I guess you could say, from 330 volts from the capacitor. And so that works out to being a ratio of about 0.014, give or take. So basically that means that for every one turn on one coil, we'd expect 0.14 turns on the other side. I've mislabeled this. This is actually should be secondary, this should be primary. But basically what this math works out to do is it tells us that for this smaller step-down transformer, we should have 5 secondary turns buried down in the middle of this transformer, and wrapped around those 5 turns in the secondary, we need to have 367 turns wrapping around in this yellow electrical tape stuff. 367 turns of copper wire going around there. And so if we have that, that gives us the right ratio, so that 330 volts turn into about 4.5, and we don't end up blowing up our LED, which would be good because we kind of would like to know when the capacitor is fully charged. So that's how that works. Alright, well, hope you enjoyed the presentation of the disposable camera computer destroyer. Thank you so much for watching.